A new kind of black hole analog could tell us a thing or two about an elusive radiation theoretically emitted by the real thing. Using a chain of atoms in single file to simulate the event horizon of a black hole, a team of physicists has observed the equivalent of what we call Hawking radiation, particles born from disturbances in the quantum fluctuations caused by the black hole's break in spacetime. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. This, they say, could help resolve the tension between two currently irreconcilable frameworks for describing the universe: the general theory of relativity, which describes the behavior of gravity as a continuous field known as spacetime, and quantum mechanics, which describes the behavior of discrete particles using the mathematics of probability. For a unified theory of quantum gravity that can be applied universally, these two immiscible theories need to find a way to somehow get along. This is where black holes come into the picture, possibly the weirdest, most extreme objects in the universe. These massive objects are so incredibly dense that, within a certain distance of the black hole's center of mass, no velocity in the universe is sufficient for escape. Not even light speed. That distance, varying depending on the mass of the black hole, is called the event horizon. Once an object crosses its boundary, we can only imagine what happens, since nothing returns with vital information on its fate. But in 1974, Stephen Hawking proposed that interruptions to quantum fluctuations caused by the event horizon result in a type of radiation very similar to thermal radiation. If this Hawking radiation exists, it's way too faint for us to detect yet. It's possible we'll never sift it out of the hissing static of the universe. But we can probe its properties by creating black hole analogs in laboratory settings. This has been done before, but now a team led by Lotte Mertens of the University of Amsterdam in the Netherlands has done something new. A one-dimensional chain of atoms served as a path for electrons to hop from one position to another. By tuning the ease with which this hopping can occur, the physicists could cause certain properties to vanish, effectively creating a kind of event horizon that interfered with the wave-like nature of the electrons. The effect of this fake event horizon produced a rise in temperature that matched theoretical expectations of an equivalent black hole system, the team said, but only when part of the chain extended beyond the event horizon. This could mean the entanglement of particles that straddle the event horizon is instrumental in generating Hawking radiation. The simulated Hawking radiation was only thermal for a certain range of hop amplitudes, and under simulations that began by mimicking a kind of spacetime considered to be flat. This suggests that Hawking radiation may only be thermal within a range of situations, and when there is a change in the warp of spacetime due to gravity. It's unclear what this means for quantum gravity, but the model offers a way to study the emergence of Hawking radiation in an environment that isn't influenced by the wild dynamics of the formation of a black hole. And, because it's so simple, it can be put to work in a wide range of experimental setups, the researchers said. This can open a venue for exploring fundamental quantum mechanical aspects alongside gravity and curved spacetimes in various condensed matter settings, the researchers write. Fake black hole might confirm Stephen Hawking's theory. Published in Physical Review Research, the study suggests the entanglement of particles on the event horizon creates the Hawking radiation. The physicist's replica has brought the science community closer to fulfilling Stephen Hawking's enthusiasm in conclusively unifying two irreconcilable theories that could, therefore, be applied universally. The general theory of relativity describes the behavior of gravity as a continuous field known as spacetime, and quantum mechanics describes the behavior of discrete particles using the mathematics of probability. A team of scientists created a black hole in a lab, and then it mysteriously started glowing. Specifically, they created a black hole's event horizon under laboratory conditions using a chain of atoms. The glow might finally shed light on how black holes radiate in the form of Hawking radiation and, in the bigger picture, the aspects of quantum gravity. The event horizon of a black hole is the point of no return. The gravitational force at that boundary is so powerful that even light, the fastest known entity in the universe, cannot escape. In 1974, English theoretical physicist Stephen Hawking, Stephen H.K., proposed a mechanism of black hole evaporation via black body radiation known as Hawking radiation. The mathematics of Hawking radiation tells us that it would take more than 10 to the power of 100, 10 raised to the power of 100, years for astrophysical black holes to evaporate via this phenomenon. Also, the energy emitted by these black holes is so less that we cannot detect it even with the most advanced technology at our disposal. This is because any signal would get lost against the noise of the cosmic microwave background. That's the main reason Hawking radiation has never been detected. But now, a team of physicists has detected similar radiation in the lab. So how did they discover it? How is Hawking radiation of black holes linked with quantum mechanics? Finally, and most importantly, how will this study bring us closer to the unified theory of everything? A black hole is an invisible place in space where gravity pulls so intensely that even light cannot escape it. The gravity in a black hole is so strong due to the dense matter being contained in a tiny space. This happens when a star is dying. In the study, a team of scientists used a single-file chain of atoms to simulate the event horizon of a black hole. What came next is something known as Hawking radiation, a theory proposed by the late physicist Stephen Hawking. What is Hawking radiation? Hawking radiation describes the hypothetical particles that arise outside a black hole's boundaries because of relativistic quantum effects. Currently, there are two theories that aim to explain the inner workings of our universe: the general theory of relativity and quantum mechanics. In general relativity, events are continuous and deterministic, meaning that every cause has a specific, local effect. However, in quantum mechanics, events produced by the interaction of subatomic particles happen in jumps, with probabilistic rather than definite outcomes. But now, this new simulation of black holes and the theory of Hawking radiation may help to unify the two frameworks. How? Currently, we have no way of knowing what happens to an object after it crosses a black hole's boundary because no information is sent back to the universe. But in 1974, Stephen Hawking said that these interruptions to quantum fluctuations may result in a type of radiation that may carry some information. And now, thanks to this new study, which showed the black hole glowing from radiation, we can analyze the properties by simulating analogs in laboratories. This can open a venue for exploring fundamental quantum mechanical aspects alongside gravity and curved spacetimes in various condensed matter settings, the study authors write. The new study comes shortly after researchers discovered a black hole that's just 1,560 light-years from Earth, closer than any other known black hole. Dubbed Gaia BH1, the black hole lives in a binary star system with another Sun-like star. Scientists hope to resolve the issues between two frameworks that describe the universe, the general theory of relativity, and quantum mechanics. What we learn from black holes can unify these two models. Black holes are extremely dense, not even light can escape them. In a certain distance, not even the fastest object can escape the black hole. This region is called its event horizon. In 1974, Stephen Hawking suggested that a radiation, similar to thermal radiation, is created after interruptions caused by the event horizon. If this Hawking radiation even exists, it's too faint for us to detect it. But scientists can create black hole analogs in a lab. While this has been done before, a team from the University of Amsterdam has done something new, Science Alert first reported.